So about the late 90s, this pre-organized building block approach was pretty well founded. And I think what our work in the 90s showed that it would be possible to make a essentially unlimited number of coordination polymers with designed structures and topologies. Around the start of this century, enormous numbers of reports started to appear on coordination polymers. And that process seems to have continued. I retired in the sense the university stopped paying me in 2004. And I've been slowing down ever since. And I've just been completely unable to follow this outpouring of stuff. Finally, a few acknowledgements. My wife, my daughter, and my son for their love and support. And these two gentlemen, Bernard Hoskins and Brendan Abrahams, who did all the, well, together with the students they supervised, they did all the real science, came up with hard numerical facts. Any scientific respectability in the papers we put out is due entirely to these two gentlemen and the people they worked with. And the people on the right here are the ones who did all the work, and it's a great pleasure for me to see most of them here in Stockholm at the moment. So once again, I'd like to thank the Swedish Academy and the Nobel Foundation for this marvelous honor, and I thank you for your kind attention.
Thank you, Professor Robson, for that very fascinating talk. So it's time for our second laureate, Professor Susumu Kitagawa. He was born in 1951 in Kyoto, beautiful Kyoto in Japan. And in 1979, he was awarded a PhD degree from Kyoto University. And then he went around a little bit in Japan, and after a while he returned to his hometown, where he's now professor at Kyoto University. By that, please join me in welcoming Dr. Kitagawa up on stage.
First of all, I'd like to express my gratitude to the Royal Swedish Academy of Sciences and Nobel Committee for the honor of a lifetime. I'd like to thank everyone for being here. It's a great honor, and it's so wonderful to see my friends, colleagues, and my family here today. So let me start my talk. My talk contains three parts. The first one in current world. In 19th century, human created new technologies that consumed a lot of energies. That time, people used coal as energy resources. In the 20th century, liquid petroleum was used. In this century, depletion of the underground resources has become a concern. So gas substances should play an important role, the trend is shifting from solid, liquid to the gas. So we are standing at the gas age. So this is small gas molecules. And usually in the ambient condition, the gas state, they are widely distributed and deeply related to environment, natural resources, energy, and life. However, humankind is still not in control of gases. So our world is dependent on the underground resources, I said. So it's a crisis of depletion of underground resources and also the global warming. So we have to switch our new world to the new world. That is the world dependent on the ubiquitous resources. However, the gas substances easily diffuse and invisible, and some has short life and toxic. So it's very difficult to handle gas substances. So we have to develop new material to control these gas substances. That is porous materials. By using this, we can carry out separation, storage, and conversion. So we have to develop new technologies in this process at low energy and the ambient condition, mild condition. So let me tell you about the history of the porous materials. In the Egyptian era, people already used the porous materials, that is activated carbons. In the 18th century, the natural stone containing the porous structure were found, and the artificial synthesis, later on, the artificial synthesis of these materials strongly contribute to the current, the petroleum industries. So quite interestingly, and Alfred Nobel invented dynamite here. So he used porous materials, natural products, that we say the Kieselguhr. And previously, I told about the importance of the gas technology. So we have to develop advanced porous materials. That the materials and the porous metal complexes I want to talk today. So about the morph materials, so already Professor Richard Robson talked about this one. So this is constructed from the metal ions in the organic molecule. And so the variety structure we can get. So I told you about the ubiquitous gas. Air is the ubiquitous gas, as you know. Air contains the carbon and oxygen, hydrogen, nitrogen as the elements. So from these elements, we can prepare many various types of things. To do this, we have to develop advanced porous materials. We handle these gas porous compounds from the process, the separation, the concentration, and the conversion in this case. So let's move on to part 2. That is the chemistry of creating nanospace. Louis Pasteur said, chance favors the prepared mind. Not by chance, but how a questioning mind opened the door to the science. So 3 notions behind my science. That is, number 1, assembly. Structure arises from elements. Number 2, space. Function emerge from nanospace. The third, dynamicity. Everything flows, nothing stays. Okay, first number 1, assembly. This is a lesson from the statistical mechanics and biomolecules. When I was undergraduate student, I learned the physics course. In particular, in the statistical physics, I encountered the Boltzmann equation. This connects the nano world, the molecular world, and our macro world. This is very fantastic. And the second is by molecules. More than 100,000 human proteins arise from only 20 amino acids. This is an astonishing triumph of molecular assembly. These insights planted me in a deep conviction that structure and function arise from assembly. The second, and also when I was the student, I saw the book, The World of Genius, written by the Professor Hideki Yukawa. He is a Kyoto University professor. He awarded Nobel Prize in physics. He loved reading the Chan-Tzu, who is the ancient old 24 years ago. He is a sage. And he wrote, "The usefulness of the useless." This is everyone knows the usefulness of useful, but no one knows the usefulness of the useless. It's very difficult to understand, but this is this notion impressed me. So, nothing useless. But if we think this is a space for the anion and the cation, in the low, very narrow in the system. So, this is nothing. But if we divide this space using the building blocks to give this kind of the closed space, but integrated to extend the infinity, this is a kind of porous materials. The number 3, dynamicity. This is a universal principle from philosophy of flow. So I learned the Greek philosophy when I was a high school student. I encountered the Heraclitus. He said, "Pantarei, everything flows." And also I was born in Kyoto and grew up in Kyoto. So I had a lot of the historical books and so on and so forth. So mostly the concept is impermanence. And the Buddhism also said, all forms arise, change, and pass away. These ideas form the foundation of my soft porous crystals I mentioned today. So let's start my 50 years journey. And I graduated Kyoto University, and I joined the Professor Fukui's group. Professor Fukui was awarded Nobel Prize in the quantum chemistry, and I learned this field, and then moved to the Kindai University, and then moved to the Tokyo Metropolitan University, and back to the Kyoto University. So each university initiate the development materials based on the 3 notions I told you. So let's start the porous materials like this. How to prepare it? So this is the famous temple in the Kyoto University, and you see this is the big balcony. From here we can see the Kyoto city. But this is constructed from 139 Zelkova trees and without pegs. This is fantastic. In the macro scale, we can make it. What about the nanospace, nanoscale? So this is 3D imagination using toy. So in this case, we have a magnet. But do we have a magnet in the nanoscale world? Yes, we have. That's a coordination bond. Coordination bond connect to metal ions and organic molecules like this. So you have the organic molecule and the solution and the metal ion solution mix. In a seconds, you can get this kind of framework. And also the crystal, very beautiful. For instance, this is 1 millimeter crystal. So the crystal structure like this, the unit is 1 nanometer. So the one side has 1 million channel. and the vertical side also 1 million. Totally 1 trillion channels per 1 millimeter crystal. That's enough for the adsorb, the capture the gas materials like this. So after graduation, I got a job and the assistant professor in the Kindai University, where the Professor Munakata conducted the kappa-1 chemistry. I also carried out kappa-1 chemistry. So from the theoretical field to the experimental field. So what is kappa-1? What we usually see is kappa-2, metallic kappa and kappa-2 salt and kappa-2 compound. What we rarely see is kappa-1. So unstable, elusive, easily oxidized, invisible in everyday chemistry. So this looks like a useless metal ion. But no. MOF originated from the chemistry of kappa-1. The Saito synthesizing, the long time ago, Saito synthesized kappa-1 nitrile ligand system. That is the network structure. This is a fully intermediate system. So after that, Professor Robson synthesizing diamond-like structure. This has no intervention, accommodate ion and the organic molecules. So he also showed the network formation principle. So simultaneously, Huni synthesized this kind of interesting materials that is using the DCNQI ligand. This NCQI ligands, DCNQI ligands has a column to show the high conductivity. This is the metallic conductivity. And so I was very interested in this system, and then we interested in the fully densely packed structure because the conductivity pathway, the dense structure is good for these properties. However, one day I tried to determine the crystal structure with my students in the Kyoto University Computer Center. The center was so crowded. I have to wait for a long time, for 1 or 2 hours, to analyze this data. In that time, we just analyzed the intermediate structure. The student said, there is a hole in this structure. I was so impressed, excited to see, because in the cavities, there is an ion and also organic molecules. So this moment marked my first step toward MOF. However, mostly the cationic frameworks are synthesized so far. So the anions incorporated. And also the kappa-1 and the ligand binding energy is not so large. So this means not so strong bond. So our central question at that time is, can organic-based coordination polymer complex, the crystals possess stable nanopore that can adsorb small molecules? That's the point. This is the research time flow. At the beginning, focusing on the densely packed structure, and after the event, I told you before my slide, and we focus on the porous structure. So move on to the Tokyo Metropolitan University. So instead of kappa-1, we use cobalt-2 plus ion to construct this kind of network structure. So without gas, this structure maintained the pore. So we carried out gas absorption. We are very succeeded in this case. But this is very exciting original report by my student, Mr. Yoshinotomi, at the group seminar, October 20, 1995. He showed this crystal structure, and in addition, Dr. Kenji Seki, he's a collaborator in the Osaka Gas Corporation. He measured gas absorption, and he sent us the raw data by fax. This is the data, okay? So it was very exciting in that time. So this similar time, the Omayagi also synthesized this kind of robust framework using zinc and benzene dicarboxylate. So now we have this type of the robust porous materials. We call this is second generation MOF material. So thanks to these properties, there are many, many functionalities that many people discovered. So move on to the Kyoto University, back to the Kyoto University, where I am very interested in dynamicity. So once again, Pantalei, okay, this is my mind, in the prepared mind. So that time, our focus is the materials from rigid framework to the dynamic porous solids. Before I'm talking about this, just a little bit, I want to show an early scientific validation. The coordination structure are dynamic rather than static. The first one, when I was a graduate student, I studied this kind of dihistidyl cobalt compound. This is crystal structure, very rigid. But in solution, in the aqueous solution, this is highly dynamic, depending on the pH. The second one, I worked for the alkaton and the synthesizing dimetal complexes. So this is a green crystal, very beautiful, but just heat, this color turn to the brown. So what's happening is dimolybdenum unit rotate by heat. This is a solid, but still dynamic. So this is very, very impressed me. Okay, move on to the framework. So just imagine this kind of things. Framework should also flexible. So we predicted the presence of the soft framework, and we did the preliminary experiment. But soon after, the various type of the flexible structure was obtained. Here, this is the 2D system, but the mutual dislocation gives this. This is the hinge type system, and this is expandable case. And this is interpenetration, like this. So many systems have been synthesized. So the one example is our case. We synthesize kappa using kappa 2, synthesize this kind of system. And when introduced gas, abruptly open up the gate and reduce the pressure, gate close. So what is important is this shows us hysteretic sigmoidal curve, completely different to conventional IPAC isotherm patterns. So we can distinguish the supercritical gas like this and at room temperature. If we exclude out summertime calculation, in particular in the energy in the open home and the closed home, the energy difference only 4 to 5 kJ per mole. So that means that this is a cooperative phenomenon. So now we have 3 materials, in particular in this third generation compound. So dynamic framework is most outstanding and unique features. So we term this a more generic term, the soft porous crystals. So the part 3, I'm moving. So I want to show the very fantastic functions about soft porous materials. And the first one, So there are 2 types of the flexibility. First one is the dynamic, global dynamics. The second one is local dynamics. So the first one, this is the acetylene gas. Acetylene gas is dangerous. If we compress the 2 bar at room temperature, abrupt explosion occurs. But we are so brave to accommodate the acetylene in our MOF compound. And finally, we succeeded in getting this type of the acetylene sorption and the storage materials. But for the usable material, we need to control the gate pressure. So the sorption is like this, but we have to use acetylene again. So we need to control the gate closing pressure. So what is difficult is the pressure range is very narrow, larger than 1, lower than 2 bar. How we can control this one? So our strategy is to accommodate gas molecule. The structure should change to accommodate gas molecule. So the deformation energy control is very important. So we did. Here, the interpenetrated structure, the unit has the zinc and benzene dicarboxylate and the pyridine. So control the repulsion energy. So we introduce the substituents, just like a solid solution structure. And finally, we obtained this type of beautiful solution like this. This pressure range is larger than 1 bar and lower than 1.5 bar. Very safe storage system we can get. The second one is the local motion. And this is the difficult, the pair for separation. That is H2O and D2O. Both have the very similar chemical and physical properties. So this separation is a sort of the 100 years puzzle. And this by electrolysis, the D2O was obtained from the natural water, tiny amount, but for the industrial production, and this is the distillation, this is the electrolysis, we need to have a huge factory. It's a very energy consuming separation system. Because the separation factor 1 means theoretically impossible to separate. Only small difference, 1.05, 1.2, even in the current system is 1.2. So we need to develop more about this mechanism or discover this mechanism. So this is a big issue. So we synthesize this type of porous structure, big pore and the small channels, big pore, small channel. On the small channel, we put this type of the local motion ligand. So the motion is just like a dragonfly. So using this channeling system, we try to separate these materials. So this is the results, and the H2O diffuse much faster than the heavy water in our system. But usual zeolites, activated carbon, HKUST1 MOF, ZIF7 MOF, and the other MOF materials show the exact same diffusion. So we succeeded in this kind of the discrimination of these materials, the separation factor up to 200 at room temperature. So this kind of flexibility, the dynamics is very important for the very difficult tasks. So at the moment, and very recently, we had a big sort of the question, because in 1997, this is very important, our materials. We carried out first demonstrated gas sorption, but without gas here, this structure, the pore size is smaller than the gas molecule here, for instance. How gas molecule accommodated in this way? This is a big issue. So we revisited these materials, and this case is the CO2. CO2 adsorbed at the lower pressure region and smoothly adsorbed. And what is interesting in the second, this pressure abrupt adsorption occurs here. So we determine the crystal structure. We can see the adsorbed CO2 molecules. Why this happens? So the result, two distinct behavior coexist. That is local flexibility and the phase transition, global dynamics. In particular, in the local flexibility, and this is the narrow channel. So narrow channel aperture like this. this is constructed from the bipyridine and the nitrate gate. So bipyridine rotate like this. So therefore, this gas molecule can diffuse easily. We call this is poor squeezing diffusion. So conclusion is, our compound at 1997, born to be soft, born to be soft. Very interesting. Already I found, but I did not know that. So, summarize here, each university initiated the development of porous materials based on this concept. So now realize, when I was a graduate student, I thought this kind of notions. So, and here, at the beginning, I showed you this kind of the functionalities. So many researchers discovered this kind of functionality, the storage, capture, and also the separation and the synthesis on the polymer and the catalysis, and also the physical properties in the ion conductivity, in the magnetic properties, and also the optical properties, and also the different type of absorption profile. So this is very fantastic, but still the application we can expect. So from the robust framework and the flexible framework, in addition, these frameworks, we are now developing this type of the hybrid morph system, using the other materials. So this is very important for the practical use. So the keyword in the assembly, space, dynamicity. These are very, very important for in the keywords in the porous materials, in particular in the morph materials. So we can expect expanding this functionality more and more, and also the commercialization just started. And the good news is still now we have more than 55 startups in the world. So these startups contribute to the scale-up production, and also the low cost morph materials. So I am the fundamental scientist. I handle only less than 1 gram materials. So for the commercialization and the transfer to the society, we need to have kilogram or ton scale materials. So it's a good teamwork from fundamental and the startups and also the society. So this is very nice, the case. Okay, so at the beginning, I told you the gas materials widely distributed and the closely related to the various aspects in the environment, energy, and also in the our body control. So, even so, we need to develop new society, new world, depending on the ubiquitous materials. So in a sense, if we can use air, so we can say the gas age is from real gold. Real gold is just gold. Right now the price is high. All the people are interested in that. It's too short range. But the black gold is coal and the petroleum. And now it's air gold, or future air gold. We need to use air. So even in the small countries, air is equally distributed. That's very important for our future. So, and I would say in the Chantzu, at the beginning, I told you about the usefulness, useless. But he also said here, and the living by use of mist. So, what is mist? So, mist is the contains the air and the water, contains everything. So, 2,400 years ago, he thought something about this, but that time it's not just a dream. But now, it's not dream, in particular in the future. So we are standing in the future, toward the future. The air gold and the porous materials, of course, in the not only the MOFs and the related MOF materials and porous materials, porous materials make our dreams come true. That's very, very important for the future. Okay, so this is my academic network. So prepared by my collaborator and the Minshu Yao, and so maybe it's difficult to see the name, but later on, please look at this. So this journey was never mine alone. It was worked together by collaborators, postdocs, students, funding agencies, institutions, and my family. My deepest thanks to all of you. Thank you very much.
Thank you very much, Professor Kitagawa, for that very dynamic and very useful presentation. Thank you so much. It's time for our last but not least speaker, Professor Omar Yaghi. And Professor Yaghi was born in 1965 in Amman in Jordan. And after a while, he went across the Atlantic, and in 1990, he was awarded a PhD degree from the University of Illinois at Urbana-Champaign, or UIUC, in the USA. After that, he moved around a little bit in the US, and finally ended up at the University of California at Berkeley, where he is now active. So by that, please join me and invite Dr. Yaghi to the stage.
Thank you. Okay, thank you, Olaf, for the introduction. And I also want to thank the Swedish Academy of Sciences and the Nobel Foundation for bestowing this honor on us. And it's a tremendous honor. And I want to thank all of you for being here. I want to share with you the journey that MOFs have realized, and that is a journey of molecules to society. It is not very often that chemists can move from molecules to society, but metal organic frameworks, fortunately, we have been successful in plotting this path and following this path. What are the key developments along this way, the key discoveries that made the field what it is today? That's really the subject of the first half of my presentation. And the second half is what does the future hold, at least some of the future. I was fortunate to have a student, her name is Guanming Li, when I first arrived to assume my independent position at Arizona State University back in the 1992, that she insisted that she wants to work in my group. And I haven't even opened the boxes. And I discouraged her from joining my group because I thought she could do better with a more established professor and can publish much more quickly. But she insisted, and I kept pushing her away and coming back. And I will return to Guanming, but she started working with these things, metal organics, just like the ones you have been listening to for the last hour. Copper-1, that figured prominently in both Richard Robson's talk and Susumu Kitagawa. And this bipyridine linker, it's a neutral linker. That's a key word that I want you to remember. And again, she made this, showed it to me, and I said to her, I don't want you to work on these things. They are not very useful, okay? And remember, I was a young professor trying to make tenure. So I wanted to make sure that I do something new and useful. So the reason I discouraged her, needless to say, she didn't listen to me, which was in the end, it worked out well. The reason I said I'm not interested in this is because it's already been done back in 1959. People have used copper-1 with adiponitrile to make metal organic, what they called coordination networks, or not yet coordination polymers, but coordination networks. And you can see this is a diamond-like network, right? And this was already mentioned by Susumu, that a German report showed very similar strategy with copper-1 and this roughly, let's say, linear linker to make the same kind of network. And when I was a graduate student, I saw this report when it came out by Richard Robson. Again, exactly the same kind of network, made in the same way, same metal ion, and the linker is a neutral linker. In this case, a tetracyano linker, as Richard described. But in Richard's paper, I thought it was very interesting to me as a graduate student that he started talking about how one could expand the linker. You can make a longer linker, perhaps. Perhaps you could use other metal ions. And as a graduate student, I found that variability to be very refreshing because people who worked on materials, this type of control was not possible. So those ideas put forward by Richard Robson and later acted upon by Richard Robson were very nice. But there is nothing new under the sun because there were previous reports that they were not too dissimilar from what Robson did. But his paper, which I encourage all of you to read in 1989, outlined some ideas that at least a graduate student such as myself found interesting. So back to Guanming and her coordination network is that they were beautiful but frail. That was the problem with the coordination networks that preceded what we call MOFs. And beautiful is great because I love beautiful objects. And in fact, I went into chemistry because of the beauty of molecules. Then we came across the report by Susumu Kitagawa with another coordination network. And there Susumu showed that he could, under pressure, have gases permeate through the structure. Under high pressure, as he just described. So there were two reports here that for me as a young graduate student and a young professor, sort of opened my eyes to this area. And I want to give tribute to my PhD advisor who taught me that science begins with doubt and questions. And that is so true. And that I was taught in graduate school, and I started acting upon it at this stage of my career. So the report by Susumu raised, in my mind, two important questions. One, are the pores homogeneous in size and shape? Pressurizing compounds does not give you, under high pressure, studying gas adsorption under high pressure, it does not give you this answer. Okay, so that was a question we needed to answer. And then we also had to answer this question: do the pores remain open in the absence of any molecular guests? Those are two very, very important questions. The first question is saying, do I have a system that has homogeneously sized and shaped pores so that I can selectively remove molecules that would fit in those pores? If you have a different wide distribution of pore sizes, then it would not be selective. So that was an important question. And the other question is, can they remain open, like this architecture? When we leave this room, the architecture doesn't collapse because it's robust. And so those two questions needed to be answered. And so far, no experiments were done to answer those questions. So my approach was, the obvious thing to do is to say, instead of those frail frameworks that are made from weak bonds, make them from strong bonds. Okay, so we started thinking about how do you make strong bonds between transition metal ions and organic linkers? Well, instead of neutral linkers, you use charged linkers, because the extra charge on the linker increases the strength almost 3 times. So the bonds that I'm talking about, as you'll see shortly, are charged linkers, and when they are bonded to metal ions, they are worth 3 times the energy that the bonds that were made in the earlier examples I've given. Okay, well, that sounds easy enough. But when you have strong bonds, something very bad happens in the lab. And that is, you make ill-defined materials, not like those beautiful crystals that were described earlier. This hump indicates that your material is completely disordered. The homogeneous pores that I was talking about, if they're present, they wouldn't be homogeneous. The framework that I was talking about that should be robust, it wouldn't be. This thing is a complete mess, and it's the antithesis of what a chemist want to do. So at that time, it was taken as an article of faith that our approach could not produce crystallized materials. We could not make crystals. So the very first thing that we needed to solve before we get to the architectures, robust architecture, we need to be able to make them in crystalline form so that we can characterize them fully on the atomic and molecular level. If we can't do that, then you can't learn anything about what you're doing. So now we come to my postdoctoral advisor, who taught me science is an exercise in optimism. So now we are facing three major problems. We need robust architectures, we need homogeneous pores, we need to crystallize the material. None of that has been done thus far, and we needed to be optimistic so that when we do the experiments and we fail, we can at least do more than one experiment and try as much as we can to make it succeed. And that brings me to this lady, Marie Curie, and her eyes. Let's focus on her eyes. This portrait sits in my conference room, and every once in a while, when things are tough, I ask the students, what do you think she's telling you with her eyes? Okay, and I think inevitably, she's probably saying to you, you can do more and you can do better. And this turns out to be a very important motto in my group, is that I think we can always, every one of us can do more and can do better. So, okay, so let's get down to what is the challenge that we needed to solve first and foremost, and that's the crystallization challenge. The crystallization challenge is a challenge where you're taking building blocks and you're stitching them together now through strong bonds, and you need to make sure that on the microscopic level that these building blocks can associate and dissociate so that they can correct their positions and make sure that you make an ordered material. If this reversibility is not present, then things will get stuck together and sometimes not at the proper orientation, and they will fall out as amorphous materials or non-crystalline. So that's one thing you need to ensure, that things can be bonded and broken on the microscopic level until they are fixed in position so that they are ordered. The second important thing is that this process of coming together and separating needed to be at the right speed. If it's too slow, then you don't make large enough crystals. Okay, you make fragments. And if it's too fast, then you make that awful hump I was talking about, this amorphous, ill-defined material. So that was the challenge that Guanming solved. She found the recipe that would take, for the first time, a charge linker, such as carboxylate, with cobalt-2+ to crystallize the very first MOF. Okay, so that was a big success made by Guanming Li. Guanming Li, remember, is the young student that came to me and I pushed her away. Now she is successful, and 20 years later,